So this is joint work, as you can see, with many people. This is because this talk will be partly a review talk on this recent aspect of multifractal analysis, which is called multivariate multifractal analysis. So I will explain what this is about. So this is actually the consequence of a long-standing collaboration with Patrice Abri, Herwig Wendt, and Roberto Leonarduzzi, who are in a signal processing team in Lyon and in Toulouse, and also more recent works with Stéphane Jaffard, with a colleague at Créteil, and Wejden Ben Nasr and Guillaume Saez, who are PhD students also at Créteil. And the recent collaboration will concern joint work with Véronique Billard and Florent Palassin, who work on physiological data collected on marathon runners, and they are at every university. Actually, this part will really be a work in progress. Okay, so I will start with giving you some ideas about what is multifractal analysis. And multifractal analysis contains the word fractal, so I will start with fractals. Okay, so I will start with a brief recollection of what is fractal geometry. And there is no precise definition of fractals, but basically it's geometry dealing with irregular sets in some way, and sets which you can get from mathematics. The two top pictures are on the left, the Mandelbrot set, and on the right, a zoom on a small part of the Mandelbrot set, where you can see the self-similarity. And the bottom are natural fractals. You have here on the left a Romanesco cauliflower, and on the right the delta of a river. Okay, so this is basically the kind of geometric object people are dealing with when when we talk about fractal geometry. And the idea is that the irregularity is a kind of loose term, and we want to quantify it in some way. And one simple classical way to do this classification, to do one classification, is by using box dimension. So you cover the set you consider by little balls of radius epsilon, and you count the smallest possible number you need to do this covering. And if you have then you perform a log-log plot regression. You look when epsilon goes down to 0 to a power law behavior, and if you have indeed a power law behavior, the exponent in the power law you will call the box dimension. So really the important word here is log-log plot regressions. This is the kind of parameters we will be looking for, exponents that can be deduced from log-log plot regressions, either mathematically or practically. Okay, so the typical example that I'm sure you have all heard about is a triadic counter set or the Van Gogh curve. And if you perform this optimal covering, you find their box dimensions. Okay, now we won't be dealing with sets, but with functions. We want to analyze data, we want to analyze signals, images. So basically things that can be modeled by either functions or functions generalized in some way, like measures or even Schwarz distribution in some cases, but basically think about functions. Okay, and you can ask the same problem. We want to study irregular functions. So I just want to mention that first the simple existence of everywhere irregular functions was not clear in mathematics during most of the 19th century. And the first well-known example were Weierstrass functions. This is a picture of Weierstrass function, of one of the Weierstrass function. And this is an unusual picture of Weierstrass, which I took when I was staying at the Mittag-Leffler Institute, and they celebrate Weierstrass on his birthday by a little party, and they have a bust of Weierstrass, and they put a crown of flowers on the bust. So this is the flowered Weierstrass. Okay, so even after Weierstrass proposed these examples, basically such examples were considered by mathematicians as very strange objects and strange counterexamples, but not to be taken account seriously, I would say. And really the impulse towards dealing with such functions, at least for modeling problems, was started by Jean Perrin. Jean Perrin is a very famous physicist, and he wrote a book called Les Atomes, The Atoms, in 1913. And there is this beautiful introduction in which there is a whole scientific program. I recommend everybody to read the introduction of this book. I mean, it contains remarkable mathematical ideas and the ideas that are behind fractals. A long time before Mandelbrot started his studies on fractals. And basically, the idea of Jean Perrin is that what you find in nature, the things that you can model by functions in nature, are things that are everywhere irregular. And basically, everywhere irregularity should not be considered as something strange, exceptional, counterintuitive, but rather as something natural. Okay, so let me show you a few examples of such data. This is on top, and this is really the kind of data which started multifractal analysis. Is data collected of Fourier turbulence, the speed of a Fourier turbulent fluid inside a wind tunnel. This is internet traffic. This is a big node which is between under the sea between USA and Japan. Okay, sorry, I have problems with my. Okay, here we are. This is euro versus dollar during 8 years, and this is 2D data. This is a density of population in a part of France. Okay, so you can see that all these data are in some way, and especially the three signals, everywhere regular, but in very different ways. So you want also to quantify, to get some tools, some parameters to quantify these differences. Okay, and down are the kind of data we are working on with Véronique Billard, which I mentioned at the very beginning. She's recording data on marathon runners, and like typically their heartbeat intervals, their speed, the cadence of their steps, and a few other. So you have also this kind of very regular data. And here's the challenge, a little bit more complicated. You would like to get also classification tools for this data, but they are recorded on the same runner and at the same, of course, during the same race. So you would like to understand how basically the singularities of each of these signals are correlated with the singularities of the other. So this is what multivariate multifractal analysis will be dealing with, not just one signal, but a collection of signals. Here we have 3 signals, but in other applications there are many more. And you want to simultaneously to quantify the irregularity, but to understand also how this irregularity is correlated between the signals. Okay, so the main tool we will be using for that is wavelet basis. So I'm just, there are many talks in this conference on wavelets. So I guess most of you know about wavelets, but in a nutshell, wavelet basis. So I'm talking here about wavelet on RD, but of course in signal and image processing, we always take D equal 1 or 2. So in that case, you have 1 or 3 wavelets, and if you pick in a clever way, and that's really the work of Meyer, Mala, Dobeschies, and their collaborators. If you pick cleverly this wavelet, you can get an orthonormal L2 basis by picking its dyadic dilations and translations by k over 2 to the j. So this is typically a few examples from a wavelet basis where you have always the same shape, which is translated and dilated. Okay, so this is actually a picture taken from the during the just after the Abel Prize ceremony in honor of Yves Meyer, where you can see Yves Meyer, Stéphane Mala, and Ingrid Dobeschies in the same row. And so they were really the starter of this theory. So why use wavelets? There are reasons which are good, I would say, for all signals and all images, which is the fast algorithms, space representations. Many large classes of signals can be represented efficiently using just a few coefficients. And what will be really interesting for us is characterization of global and pointwise regularity, because, as I said, we want to study to understand in which sense this type of data that I showed are irregular, in some sense globally, and that will be given by function spaces to which the data belong to, but also locally. We want to understand if the regularity is everywhere the same or changing from point to point in some way. Okay, and a key property of wavelets is vanishing moments, which is a very important reason very important property to analyze regularity. Okay, so the first tool, which I call wavelet scaling function, but it really comes from ideas developed by Kolmogorov in the 1940s when he was Kolmogorov, when he was for a short time a physicist during the Second World War. He worked on turbulence and introduced what is called the scaling function. And I'm just reformulating what he did in a wavelet language. So we consider the wavelet coefficients, so just the coefficients of the function we consider on this orthonormal wavelet basis. And what we consider is just little LP norm at each scale. So 2 to the minus j is the scale of the wavelet, basically the width of the wavelet. And so we sum all wavelet coefficients at each scale, but we consider not just sums, but little LP norms. Okay, so actually little LP averages. You have about 2 to the dj coefficients, so you divide by 2 to the dj. So this is what we call the structure functions. And again comes this idea of a log-log plot regression. We in the limit of small scales, we look for an exponent like that. So if such an exponent, if you don't have this scaling behavior, you take a limit of quotients of logarithms to get something well-defined, mathematically well-defined. But this is really the idea. Okay, so this is the equivalent in a wavelet formulation of this first tool that was introduced by Kolmogorov in the 1940s. And so you have, for those of you who like function spaces, you get an easy interpretation of this scaling function in terms of function spaces, in terms either of Sobolev spaces or Bezov spaces. Just using, this is an easy exercise if you know the wavelet characterization, for instance, of Bezov spaces. So what it really means is that it tells you, if you fix a little p, it tells you how smooth the data are in the Sobolev scale. Okay, in particular, if this scaling function is strictly positive, your data can be modeled by an LP function, and if it's negative, it cannot be modeled by an LP function. And this will be relevant in the following. Okay, once again. Okay. So what is this? What is the advantage of using this wavelet scaling function as classification parameters? Okay, so that's a first tool for classification that is used in signal and in image processing. And okay, a key property is these log-log pot regressions, which makes them actually easily computable on real life data. And you have some, I would say, mathematical properties which are good. The fact that, of course, if you change the wavelet basis, you are using the scaling function does not change. It doesn't depend on the tool you are using to make the analysis. And it has some robustness properties. If you add a smooth function to the data, or if you do a smooth deformation of the data, it does not change. And this is just because of this function space interpretation. And something which is very nice also is that this very last properties, if you apply it, this is not a theorem, but if you apply it to very large classes of stochastic processes, you get something which is deterministic and not random. So it means that it touches, it grasps the not just the sample path you are using, but the underlying properties of your process. Okay, so I just recall the definition of this wavelet scaling function, and this is just to show you that it can be used actually in signal and image processing. So it's nicer to show some pictures rather than some signals. So here is a very simple example, a disk where the scaling function at 1, actually for every p should be equal to 1. And first you see that you get points that are well rather well on a straight line. And if you do a standard regression, you get something very close to 1. And something a little bit more complicated, which is the characteristic function of a von Core snowflakes plus a polynomial trend. And what you should get is this value on the top here, and you get, as you can see, you get something also very close, which shows, at least on these two toy examples, that indeed numerically you can get things with some precision. So this is a real life picture, which is very rough in terms of function spaces. Because of this, you see these very strong oscillations due to the stems of the trees and the very oscillatory texture. And this is an example. These are the log-log pot regressions. So it's not perfect. You always have problems at the small and large scales, but you get enough, I would say, enough middle range scales, which are on a straight line to get precisely, again here for q equal 1, a good regression, and this yields the scaling function. So here, and this is again one of the worst cases we worked on. You see that the scaling function is always negative. Which means that you cannot model the data by functions belonging to any LP space, no matter what P is. What I forgot to say is that if Q, I often mix P and Q, as you will see. So LQ spaces, if Q is between 0 and 1, we replace LP by the RD spaces HP. I don't want to go too much into that. Those of you deal with function spaces know what I'm talking about. The simple reason is that for p less than 1, the wavelet characterization of LP becomes the wavelet characterization of HP. So in a sense, it's a natural substitute if you want to work with parameters between 0 and 1. And these are smoother functions that are French saucisson, which if you have come to France, you've certainly tested this. And this is much smoother, as you can see. These are log-log plot regressions, again, for Q equal 1. And this is a wavelet scaling function, which is positive for essentially all values of Q, at least in this range. I think it's positive for all values of Q, okay? So this is also to show you that different kinds of images are very different wavelet scaling function, and you can indeed use that for classification. Okay, so I'm coming back to my marathon runners, and here is one example of wavelet scaling function for a marathon runner. So it's interesting because you can see that the wavelet scaling function is first positive and then goes below 0 for Q about 6 point something. So the data belong to LP for P less than 6 point something and do not belong to LP if P is larger. Okay, so that will be important in the following also. Okay, so another parameter we will have to use is what we call the H-mean, the uniform Holder exponent, which is basically, instead of considering subarray spaces LPS, we consider global Holder spaces C alpha. Okay, and you look at the maximal regularity inside this class, and this is what we call H-mean, and it's also computable by log-log plot regressions of wavelet coefficients. If you take the supremum at each scale, this is this omega j of the wavelet coefficient, and you perform a log-log plot, then you get the H-mean. And the point is that if it's positive, then you are modeling. You can model your data by continuous function. If it's negative, then the function is not locally bounded. Okay, so we have this collection of parameters, and here are just a few examples of their use. One problem that mathematicians dealing with in mathematical finance, which is not completely settled now, is what are the stochastic processes which can model the data? And here I come back to this euro versus dollar values. And if you compute locally on 3 months windows, the H-mean, you get something like that, which tell you that it's most of the time below 1/2. So in particular, it's really rougher than the regularity of Brownian motion. And if you try to model your data by processes which are deduced from Brownian motion, it won't work. But you can also see that maybe, except at some exceptional points, it's clearly positive, which means that you have some uniform Holder regularity, and you cannot model this type of data by jump processes, for instance, which is a modeling which is much used in finance. So this is a kind of use that you can do of these parameters to eliminate some models that do not fit that are not compatible with what you can compute on the data. Okay, and this is heartbeat interval. So this is really not new. This is a kind of applications of regularity IDs, which has been going on for a long time. If you look at so here you model the time intervals between 2 consecutive heartbeats of a person, and you make a recording during 1 day, 1 complete day. And this is a healthy versus healthy person versus a person which has some heartbeat failure problems. And you can definitely see it on the H-mean, which is very close to 0 in the first case, and significatively negative. These are the log-log plot regressions, you see. and significatively negatives in the heartbeat failure case. Okay, so this is an old application, but this is a recent one that we just worked out on these marathon runners. And one interesting question that we want to address from these recordings of marathon runners that Véronique Billard and her team are collecting is, okay, from all this recording, what can we say to the runner about his race, and in particular what can he improve? And for instance, a naive first answer was, okay, he should try to stay always at the same speed, but this is not true. Somehow there are moments where you feel a little bit better or a little bit less well, and if you impose the runners to have the constant speed, then it's not efficient. It's much more demanding for them. So another idea is that maybe naturally there are some modifications in the speed, in the heartbeat, because it's, I mean, a runner is not a machine. It's a real living person with some fluctuations. And maybe what we can check is not things, values of parameters which are constant, but rather if there are some modifications in the fluctuations in some way. There must be natural fluctuations, but maybe they should be the same in all the moments of the race. So one first investigation we made is to make a multifractal, I mean, this kind of multifractal analysis, this computation of H-mean, for instance, or of the wave scaling function at the first third of the race and the third of the race, and to see if there are some modification in these parameters. And indeed, from some runners, there are very few modifications. H-mean is essentially the same, and this is an interesting case where they are very different, and you see that it goes up. So it means that it's negative, as is often the case for heartbeat. But it goes down. I mean, it goes up in absolute value. So it means that basically the data are getting less and less regular in some way. Okay, and the fact that there is this rather effective difference between different periods of the race, probably, I mean, this is really an investigation which is just beginning, but seems to be correlated with the fact that, I mean, good runners manage to have kind of constant parameters of that sort. Okay. Now we want to go a little bit beyond this wave scaling function and this computation of H-mean, which are good parameters for classification, but in several applications are not sufficient. So one typical application, which is really the driving motivation of all the subjects, at least in the until the 1980s and 1990s, is the analysis of turbulence. And if you I won't show examples because that would be too long, but basically you cannot see a difference between several mathematical models supposed to model turbulence if you look at the H-mean or at the wave scaling function. So people wanted to go further, somehow to have more information than what is supplied by wavelet scaling function and this uniform regularity exponent. And these new developments are really motivated by seminal ideas introduced by two physicists, Uriel Frisch, who was a specialist of turbulence, and Giorgio Parisi, who was a specialist of statistical physics, and who suggested that there must be some connections between these kind of global regularity parameters, They tell you, again, I gave this interpretation in terms of Sobolev or buzzer spaces, and the pointwise singularities that you can find in the data. Okay, so I will say a few words about pointwise regularity. So the usual definition, the standard definition is given by pointwise Hölder regularity. You look at how big is F minus its Taylor expansion in the limb in small ball centers at X naught. And you have, so this is the one which is mostly used, but there's also an alternative, which is a generalization supplied by Calderon and Zygmunt, where you take, instead of taking, I would say, little L infinity local norms of F minus the Taylor expansion, you take little LP, you take LP local norms, and they called that TP alpha regularity. Okay, so this is okay if your data are locally bounded. This is the assumption, and this is okay if your data are not locally bounded, but locally belong to an LP space. And as we saw sometimes, you know, the data are not locally bounded, the H-mean is negative, and you have to use this TP alpha pointwise regularity. So, and you define the largest possible alpha for which you have this estimate, you call the P exponent. And if P equals plus infinity, you have the pointwise Hölder regularity, and you call that the Hölder exponent. Okay, so in a nutshell, this is the definition of pointwise regularity. This is just to give you some kind of feeling of what it means on the roughness of the graph. So these are sample paths of fractional Brownian motion, which are everywhere the same pointwise regularity, with exponents 0.3, 0.4, 0.5, 0.6, and 0.7. So it shows you in some intuitive way that, of course, the higher the Hölder exponent, the smoother the data. And it gives you somehow some idea of how rough corresponds to a given Hölder exponent, at least between 0 and 1. Okay, so pointwise regularity, you cannot really use that for classification in applications, because in many models used in applications, it is extremely erratic. Okay, so this is a sample path of a Levy motion where you have discontinuities, but also all possible in an arbitrarily small time interval. You can find all possible Hölder exponents. So it's incredibly erratic. This is also a multiplicative cascade, which exactly has the same property. So this is true for many models. And so you don't want to try to find out what is the Hölder exponent at every point. And the idea, really the brilliant idea of Parisi and Frisch was to say, okay, we don't want to know that. We just want to have some kind of global information about how big are the set of points with a given, where you meet a given regularity exponent. And they more or less showed that this is related to scaling functions. Okay. So for that, we first have the first point in the agenda is to have a wavelet characterization of pointwise regularity. So this is defined in terms of what we call P leaders. So we have to give a new terminology for wavelet coefficient. So we index wavelets not by the 3 indices that I gave before, but by dyadic intervals in 1 dimension or dyadic cubes in several dimensions. And the idea that you should keep is that basically the dyadic cube lambda is essentially the support of the wavelet. Okay, so for high frequency wavelets are indexed by small dyadic cubes, and low frequency wavelets by large dyadic cubes. Okay, so this is a little picture of what we call, of how we construct the important quantity which allow us to characterize pointwise regularity, and this is called P leaders. So it little LP norms with some ponderation of local wavelet coefficients, And what this means is that if we consider the little square here where you see the cross, then the P leader is obtained by taking a little LP norm on all the red cube here. So on all the wavelet coefficients, which are in some sense close to the little square in the middle. But they can be, it's an infinite number of them or a large number of them if we work on real life data. And this complicated formula just boils down to a simple supremum of wavelet coefficients for Hölder regularity. Okay, and the important point is that okay, if you do log-log plot regressions, local log-log plot regressions of P leaders, then you recover the P exponent. Okay, so the idea is that we should incorporate in the scaling function, we should replace the old wavelet scaling function by new P leader scaling function where we just replace the wavelet coefficient by these P leaders. And really the idea, and this is basically to make the seminal idea of friction parity correct. The idea is that it is not directly the wavelet coefficient that encapsulates pointwise regularity information. It's these P leaders. So we should incorporate P leaders in the scaling function. And then the recipe is just the same as usual. We do a log-log plot regression. And the exponent is a new scaling function, which we call the P leader scaling function. And so the important information is that it has all the good properties that already this wavelet scaling function had in terms of independence of wavelets and smooth deformation and of variables and so on, but also it's these properties also for negative values of the parameter Q. Okay, it's not only well defined for Q positive, but also for Q negative. And this is very important because okay, so I just recall here the information I gave that P leaders allow to recover pointwise regularity through local log-log plot regressions. And the important point here is that, for instance, for in the analysis of turbulence, it's the negative values of Q in the scaling functions that will allow to say which models are good or bad. Okay, so it's really something very important to go from R plus to R in the domain of definition of scaling functions. Okay, so this is an example on marathon runners. So this is typically a case where the H-mean is negative, but the wavelet scaling function is positive for P equal 2. So we can compute the P leader scaling function for P equal 2, which is this function. Okay, so this is just an example, and you can see that it does differ from the one of another runner. So you very loosely you can see that you can see differences using this P leader scaling function. And so the idea behind the argument of parity and Frisch, I will now just work it out, is that you can get you can recover information on the dimension of the set of points with a given pointwise regularity from this wavelet scaling function, okay, through what we call the Legendre P spectrum, which is just the Legendre transform of the P leader scaling function, okay, and what we expect to get is what we call the multifractal P spectrum, which is the Hausdorff dimension of the set of points where the P exponents takes a given value, okay, so what you can actually prove is that you don't have an equality between this Legendre P spectrum and the multifractal P spectrum, but you always have an upper bound. Okay, of course, you can, as I insisted, you can do that only if the wavelet scaling function is positive for the value of P that you pick. Okay, so there are, I don't want to go too much into mathematical theorems. There are two kinds of theorems where you can prove equality here, which are either generic results. If you work in a function space, you show that most functions in this function space satisfy equality in this here, or for particular specific models, typically the models that are used to model turbulence or other types of phenomena. Okay, I see that time is passing very fast, so I wanted to show you the heuristic derivation of this, but I will just go beyond that, and I'll rather show you what it gives on some data. So this is internet traffic, and this is a leader scaling function for I think P equal to 2, but yeah, I think P equal to 2, and you get a straight line here. And what it really means, if you take the Legendre transform of a straight line, so you will get just 1 point, minus infinity everywhere, except that at 1 point. On the upper bound of the multifractal spectrum by the Legendre transform just tells you that the dimension is bounded by minus infinity. So it means that the set is empty for all exponents except 1. Okay, so this means that the exponent, the pointwise regularity exponent, is everywhere the same. So that's very interesting if you, in situations like that, where you get a straight line in the scaling function, you can deduce that the Hölder exponent is constant everywhere without having to estimate it at every point. Okay, so for some data, this is what we get, and this is, of course, very, very interesting. Okay, this is the turbulence example I talked about, and you can see that this, the red and the blue are the theoretical multifractal spectrum of two different models of turbulence, and you can see that the little crosses and dots are the data obtained on real-life turbulence signal, and they perfectly fit the log normal model and not the log Poisson model. So I don't want to describe this model, but just to show you that typical applications for model selection, which you could not do using just, I would say, physicist arguments. You really need to do that. And it's obtained the decreasing part, you can see, of the spectrum, which correspond to negative values of P. Okay, so the increasing part, you cannot see the difference, and you really have to use in the scaling functions negative values of P to see the difference. Okay, so in evidence of time evolution for this financial data, for instance, if you look in the first half and in the second half, you see different spectrum showing that the nature of the data is changing with time. Okay, and okay, I wanted to show you, of course, it's difficult to do classification on a complete curve. So we extract from the curves a few parameters, what we call the H mean, which is the starting point of the spectrum here. I already defined the H mean. C1 is the position of the maximum here. So it's the average regularity. And C2 gives you some idea of the width here at the top, if it's kind of flat or very curved. And so, for instance, here are a few examples obtained from two marathon runners on the multifractal analysis of their heartbeat intervals. And the C1, so the average regularity, in the first case, you see the C1 are very close. So basically the race is similar at the beginning. The race parameters are similar at the beginning and the end of the race. And for another, they differ significantly, showing that the way he was the guy was racing is very different at the beginning and the end. Okay, and for the C2, so the width of the spectrum, C2 equals 0 means that the data are not multifractal. You just have one point, and the larger this, so here you have, for instance, a C2 which is very, very close to 0. So it means that you have almost no multifractality. All the older exponents are very close to each other. And you see a big okay, so sorry, this is the main point I wanted to show you, that okay, here you have almost no multifractality, whereas in this last part of the race, or for the other runner, you have much wider range of exponents. Okay, so this is a kind of information we can extract from this. So I'll just okay, I'm running out of time. I'm sorry. I'd rather give you some idea about what the last point of my talk, which is multivariate analysis. As I mentioned, this is really motivated by the fact that sometimes we don't have just one signal, but a collection of signals. Okay. So a typical application is MEG recordings, where now you recall you can collect signals at many points of the brains, and of course the signals you collect are related in some way, but in a not linearly or not in a statistically simple way. And the idea is that maybe using multifractal IDs, you can show that they are related, that their singularity sets are related in some way. Okay, so we have the mathematical formulation is that we have a collection of regularity exponents. For each, we have the equivalent of the P leaders, and we have so the exponents are locally given by these log-log plot regressions. And we want to know if for example, I pick here just two data, so two signals. We want to understand what are the set of points, what is the size of the set of points where the first exponent takes a given value h1 and the second exponent takes a given value h2. Okay. So this is what we call multivariate multifractal analysis. So it's just an intersection of fractal sets. Okay, and this is already at this point, if you know a little bit about fractal geometry, you know that the problem is very, very tricky, because the question related with intersection of fractal sets are extremely difficult. I mean, there are very, very few results that are known, and I mean, for simple fractal sets, it's very difficult to say something. So the bivariate, what we call the bivariate spectrum, or the joint multifractal spectrum, is just the dimension of these intersections. Okay, so it's a two-variable function, and the first simple idea, and I will just show it, is that you introduce multivariate structure function. So you take basically little LP norms, as in the case we were studying before, of the first signal, and you mix them with little LQ norms of the second signals, and you make log-log plot regression to get a scaling function, and you make a two-variable Legendre transform, and you get a two-variable spectrum, and you expect that the bivariate spectrum will just be this Legendre spectrum. Okay, so I will jump a little bit on the mathematics just to show you application of this formula. So for signals which are very correlated, for instance, a signal and itself, which is kind of stupid to do, you get spectrum on a straight line. Okay, I'll show you another picture. So if you get, for instance, binomial cascades, which are very standard multifractal models, which are positively correlated, you get exactly the same thing. This is numerically what we get. You get a spectrum which is supported on almost a straight line. But if you decorrelate them in a negative way, you get nice full spectrum like that. Okay, so this is just the idea I want to show you, is that these computations of two variable spectrum give you some information about some kind of correlations between the singularity sets of the data. And I will end with what we obtained for marathon runners. If we do the multivariate analysis of heartbeat and speed, these are the scaling function, and these are the Legendre transform. Heartbeat and speed, you can see that there are, I mean, the support is a kind of big triangles. They are very weakly correlated, but speed and cadence, they are very strongly correlated. So this is a very interesting information which was not directly available from the data and which is revealed by the multifractal analysis. Okay, I'm sorry I had to rush a little bit at the end. Here are a few references about what I talked about, and while you can look at them, I will be happy to answer questions.